According to the kinetic theory of matter, matter is made up of tiny particles that are in constant random movement and that are colliding with each other, perhaps with the walls of the container in which they are found. Based on this, matter can be classified into three categories: solids, liquids, and gases. In this video, we are going to focus on gases and try to see the laws that govern their behavior and interactions. Their behavior in particular. The first of these laws is Boyle's law. This law tells us that the pressure of a gas is inversely proportional to the volume, provided that the temperature remains constant. In other words, if you have a gas at two different pressures and volumes, then they should satisfy the relation P1 V1 equals P2 V2. If we want to plot a graph of the pressure against the volume in this case, as you can see, this is just a rectangular hyperbola, so the graph looks like this. Or if you prefer to plot a graph of the pressure against 1 over the volume, then you're going to have a straight line. The second law here is Charles's law. This law establishes the relationship between the pressure. This law establishes the relationship between the volume and the temperature. It states that provided that the pressure remains constant, then the volume of a gas is directly proportional to the temperature. Here, P needs to be constant. What this means is that if you have a gas at two volumes and two corresponding temperatures, then V1 on T1 should be equals to V2 on T2. If we want to represent this graphically, then it should look like this. So here we have the volume and here we have the temperature. So the graph looks like this. Note that here the temperature is in degrees, and when the temperature is 0 degrees, the volume is not 0. Rather, we need to extrapolate, as was shown by Lord Kelvin, to this temperature, which is known as absolute zero temperature, and it has a value of negative 273 degrees centigrade, approximately. At this temperature, all molecular motion freezes, and the gas is kind of inert, or kind of really freezed, to say it simply. So it is at absolute zero temperature that the volume of a gas is kind of zero, that the gas has no volume. In quantum mechanics, if we have a special type of particles known as bosons, which are particles that have a whole number of spin, then towards this temperature, the gas of bosons will condense to a state known as a Bose-Einstein condensate. But that's not the subject of this video. We are not talking about quantum mechanics here. It was just to mention. The third law that governs the behavior of gases is known as the Gay-Lussac's law. Gay-Lussac's law. As you can guess, this law establishes the relationship between the pressure and the temperature of a gas. So it's kind of intuitive. It tells us that the pressure is directly proportional to the temperature, provided that the volume of the gas remains constant. Again, here, if we are, let's say, measuring the pressure and the temperature of a gas at two different states, then they are related via this relationship. So P1 over T1 should be equals to P2 over T2. If there's a third state, then it should be equals to P3 over T3 and so on. So to illustrate that graphically, it's really simple. Let's say here we have the pressure and here we have the temperature, this time the absolute temperature, so it's in Kelvin. So the graph should look like this. It's just a straight line that passes through the origin if we are having absolute temperature. The fourth law, there are many laws, is the Avogadro's law. So let me just take another sheet of paper. So the fourth law is known as Avogadro's law. And this law is a really powerful one. It states that under the same conditions of temperature and pressure, the volume, an equal volume of all gases is going to contain the same number of particles. So if T and P are constant, then a certain volume of any gas should contain the same number of particles. In other words, it should be proportional to the number of particles, or the number of moles in this case. You might recall that the number of particles corresponding to a given quantity of a substance is related to the number of moles via the relation n equals to small n times L, where L is the Avogadro constant, which has a value of around 6.02, I guess, 10 to the 23 particles. So 1 mole of any gas contains this number of particles. Note that this law is very powerful in that it relates this constant, this value L is a constant for any substance. For example, if you're having carbon dioxide, CO2, which is a gas, then 1 mole of carbon dioxide contains 44 grams. So this is 1 mole of carbon dioxide. And let's say you have another gas like, let's just say ammonia. 1 mole of ammonia contains around 17 grams. So this law states basically that if these two gases are held at the same temperature and pressure, then an equal volume of the two is going to contain 6.02 times 10 to the 23 molecules in this case, because these are molecules. So this law is really, really powerful. Now, we can combine all these laws, so Boyle's law, Charles's law, Gay-Lussac's law, and the Avogadro's law into one law that's known as the ideal gas law, or the ideal gas equation. So, which tells us that PV is equals to nRT, which means that at a given temperature, the pressure and volume of a gas is related, are related via this relation, where N is the number of mole, R is the gas constant. Another way of writing this is thus PV equals NKBT. So this is just the equivalent form of this, where this time we express PV and T in terms of this constant, which is known as the Boltzmann constant, which has a value of around 1.38 10 to the negative 23 joules per Kelvin. Yeah. And here we have the number of molecules. or number of particles, if you want, of the gas. So these two forms are equivalent. Usually, in statistical mechanics, we work with this one, and in chemistry, we usually work with this formulation. Something important to mention here is that this law, the ideal gas law, just as, which is a combination, in fact, of the pre-mentioned laws, holds only for ideal gases. So all those laws hold only for ideal gases, which means an ideal gas, for short, is one that really satisfies these laws perfectly. But as you might imagine, in practice, the gases we deal with, or the gases that we have in nature, are not ideal because of intermolecular forces of attraction that exist between the particles, the molecules, such as, for example, the dipole-dipole interactions, such as, for example, van der Waals forces, such as, for example, hydrogen bonding, for those that do like chemistry, so hydrogen bonding. So these intermolecular forces of attraction lead to a non-ideal behavior. In other words, the particles are not independent. An ideal gas, in the ideal gas case, we assume that each particle is kind of independent, which means it does not interact with the other, and that's why they can satisfy all these laws really to perfection. But non-ideal gases have a non-ideal behavior due to the presence of intermolecular forces of attraction. So this law won't hold for a real gas. We need to modify it, and that modification is was brought by van der Waals. So van der Waals, the van der Waals equation, which tells us that for an ideal gas, we need to account for these intermolecular forces of attraction. So this equation modifies to P plus A on V squared times V minus B equals N R T. So you can notice that the structure is kind of maintained. We have added, however, two terms in the pressure and the volume. So the first term, the A here, accounts for the intermolecular forces of attraction that I mentioned earlier. And the B accounts for the fact that the volume actually is finite. The volume of gases is finite. So we need to kind of account for that in this equation. So this corrects the non-idealness of gases in general. So hope this video has been able to give you a clear view of of the laws that govern the behavior of gases: Boyle's law, Charles's law, Gay-Lussac's law, the Avogadro's law, and then the ideal gas equation given by this, and then how it's corrected for non-ideal gases to get this equation. If you enjoyed it, hit the like button and subscribe in order not to miss upcoming similar content. And remember that physics is the belief that a simple and consistent description of nature is possible. That's what we are trying to do with all these laws.